Hey, what's up, guys? Chung here again. So today, let's take a look at this LeetCode problem here. Number 220 contains duplicate number 3. So this one gets a lot of like downvotes. I'm gonna give it my own upvote. Okay, so you're given like an array of integers, okay? And then you need to find out whether there are two distinct, basically, if there are two different distinct indices I and j in the array such that the absolute difference between the numbers I and numbers j is at most t, and the absolute difference between the I and j is at most k. Okay. So for example, this one, right? So the difference between those two numbers has to be 0, which means they have to be the same, right? And the difference between the indices has to be at most 3. So in this case, this index is 0, right? This index is 0, 1, 2, 3. So this 1 and 1 happens to be our answer, right? Happens to satisfy the conditions, those two conditions, basically uh, I minus j. Okay, the absolute value is smaller, greater, equals smaller than the k, and the numbers, right? The numbers I minus numbers j, okay, is smaller than t. Basically, those are the two conditions we're trying to satisfy here, right? And so the first one, those two ones can satisfy both of the conditions here. And second one is the 0. So it's 2. So basically anyone can, and the difference is 1. Mm, difference is 1 means actually basically any of them can satisfy this condition, right? And here it is false, right? So the difference is 3, but as you guys can see, the minimum difference is 4 in this case, right? So there's no way we can find the two indices, right, whose difference is less than 3 here. That's why it's false. Okay, so so I think today I'm gonna introduce a few different solutions, right? So the first one, obviously, is brute force. Okay, so basically, I mean, since the index, since the condition one's here, basically what we need to do is we need to maintain like a sliding window, right? Basically, we're gonna maintain like a sliding window whose size is k. Okay, and every time when we have like a new starting point, okay, let's say when we start from 1 here, we need to basically we're gonna scan, right? We're gonna scan the next two elements, okay, and we will see if any of them, right? If any of them has the difference, right, between the current starting point is smaller than t, then we know we found the answer. If we cannot find those such candidates, right, in the end we simply return false. Okay. Mm, yeah, that's the brute force. But in this case, if we use that one, so this problem is going to be TL timeout, because that problem, as you guys can see, depends on how big the k is, right? And basically the time complexity is going to be the n times. So each time we're gonna scan k elements, right? So it's gonna be n times k. If the k is the same size of the n, right? So and then the time complexity is gonna be n squared. Basically, that's the first brute force way, right? And a second, right? A second option here is that, you know, let's say we have a like different numbers here, right? We have different numbers here. Okay, I'm gonna randomly draw some numbers here. Let's say the sliding window is this. Let's say we are maintaining like a sliding window here. So that's a sliding window. Okay. Mm, um, yeah. So Maybe I'll draw a little bit more here. Let's say the sliding window is this, okay? That's the sliding window. I mean, if let's if the numbers within the sliding window is sorted, okay? If it's sorted, and let's say we're trying to find, uh, let's say we're trying to find 3 here, okay? Let's say 3 is our current number, and we have like oh, and the sliding window, right? Let's say the k is like mm, the k is 5, right? K equal to 5, and our current number is 3 here, right? And if these 5 numbers they are sorted, okay, then with the current 3 here, it's very easy for us to find uh, to find the current condition, because since we're maintaining like a k size of sliding window, so the condition 1 is always met, and we just need to find if there's a number, right, whose difference is absolute difference is smaller than t. If this like 5 numbers they're sorted, right? So all we need to find is if we can find the previously number. Let's say there's a previously number 1 here, n1, n2, okay, n3, n4, and n5. Okay, assuming this 3 here, the number 3 is just right in the middle of this sorted 5 numbers here. Okay, if that's the case, right, actually all we need to check is we just need to compare the difference between the previously basically the previous number and the difference between the next number. Okay, why is that? Because they are sorted. Okay, they're sorted because which means n2 is bigger than n1. Okay, which means that if the difference between the n2 and n3 is greater than t, okay, then the difference between n1 and n3 is definitely even greater than t here. So we don't have to worry compare with the rest of the numbers here. Same thing on the other side, okay? Because n5 is greater than n4, so we just need to check if the neighbors if the neighbors of the 3, if any of the neighbors are within the range of the t here, then we know, okay, we found the answer because they are sorted. Yeah, and now the question comes to how can we maintain this sorted array here, right? I mean, we can always, every time we have this one here, we can always sort, but that's even slower, right? To sort this k numbers, right? If we do a sort method every time we have a new numbers here, it's gonna take like a k log k time, right? So it's even slower than the k here, than the brute force way. And so one of our options is to use the what is that? The binary search tree provided in Java, because in Python there's no built-in binary search tree implementations. So I mean, we can of course use like build our own like binary search tree in Python, but that will be too much of the code. So the first solutions today I'm gonna show you guys. I'm gonna switch to the Java, so I can use the built-in like tree set to maintain the difference. Okay, yeah. Okay, cool. So let's try to code the first one, Java version. So I'm gonna switch to the Java here. Okay, so in Java, there's like a data set called tree set. So and here I'm gonna I'm gonna initialize with a long type instead of integer. The reason being is because in the test case there are like some like very big test case that has the biggest value of the integer, and if we're doing that and we do a minus t here, it could be out of the range, right? That's why I we just to avoid that things, we're gonna convert all the integers to the long type, so that we don't need to worry about the the values out of the integer range. Okay, so set. Okay, it's going to be actually the tree set, right? So the tree set uh, goes to what, the new tree set. Okay, so same thing here. Yeah, so it's the Java, we have to remember those semicolons here. So like I said, we just need to for like okay, sorry, for I equals to 0. Okay, and I is smaller than the nums dot length. Okay, I plus plus. Okay, uh, so basically for each of the number, right? So for each of the numbers here, we're trying to find the with the tree set, there's like two functions we can use, either the ceiling or the floor. Okay, so the tree set basically is a balanced binary search tree, right? Basically, the ceilings will give you the okay. Let's try to find the floor. Okay, so uh, 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 floor. Okay, floor equals to the tree set dot floor. So this floor will give you the biggest number that's on the left, basically the neighbors of the numbers I on the left. So number side. Okay, I'm gonna do this, right? Basically, if you pass in like this current numbers here, the floor will give you the left neighbor of the number here. Okay, and basically if the floor, we check if the floor is not null. Okay, basically if there's no such numbers, so this floor will be null here. And what? And the since the floor is a smaller number of that, right? And number minus floor, okay, it's within the range of t, okay. So if that's the case, right? Sorry, I will simply return true. Okay, same thing for the right neighbor, which is going to be the ceiling. Okay, ceiling of tree set dot ceiling number. So the ceiling will give you the right neighbor of the of the current number. So same thing here. If the ceiling, okay, it's not now, and the ceiling, okay, subtract the number, right? It's within the range of t, okay, and then we also return true. So that's the two step. And the next one is we need to insert, right? Basically, we need to insert the current number into the tree set. Tree set dot add number. Okay. Yeah, I think yeah, those. And the last thing is we have to maintain the size of the case sliding window here, right? Basically, we're maintaining like a sorted case size of the integers here. So basically, if the I is greater than k, okay. Sorry, I have been coding in Python for too long, so I have to get kind of getting used to this. I need to get used to this Java style here. And tree set dot remove. Okay, we need to remove which element, right? Numbers of the I minus k, right? So that's how we maintain the maintain k size of binary search tree. Okay. Yeah. And then if nothing happens here, we simply return false. Okay. Yeah. Oh, and okay, and I think we need to do some like conversion here because the number, it cannot explicitly convert the integer to long. That's why we have to do some conversion here. Mm. Okay. So yeah, I think that's pretty much it is. Let's try to run the code here. Ah, semicolon here. Int long integer. Okay, cool. So submit. Hmm? What? Uh, uh, floor. Okay, we have a floor here. Floor num ceiling. Oh, sorry. Here. Ah, maintain the size of that. It's not I here. It's the tree set dot uh size. Yeah. Yeah, sorry, it's not it's not the index. Okay, and that's yeah, cool. So yeah, it passed. All right, and yeah, I mean, so the time complexity for this is so we have a O n here, right? We have a O n. Sorry, we have a n times here, right? So the floor. So this is a log n, right? So the floor is log n. The log n here, and sorry, it's a log k. Sorry, not log n, log k, because we are maintaining a size of the k BST. And here is also for log k, and also here, right? So also log k. Basically, the the complexity, time complexity will be the n of log k, and the space complexity will be a O of uh, basically the minimum of the k, n of k, right? It's not a, it depends on like who is smaller, okay? Either n or k. Yeah, so that's the first approach basically we're doing here. We're utilizing a tree set, right? A tree set in Java to maintain like a sorted size, sorted integers, right? Sorted integers of size of k. Okay, and we'll just use, since it's sorted, we can simply compare the left and right neighbor with the current number to check if that is the, it can satisfy with the second condition, right? Which is this one. Okay, cool. So that's that. And okay, and another even better way is to use the bucket idea here. Okay, so I think it's this. We're borrowing the idea of the bucket sorting. For the bucket sorting, if you guys still don't know what the bucket sorting is, basically we're having a range of the bucket here, right? Range of bucket here, and let's say from 0 to 9, okay, 10 to 11, 10 to 9, 19, okay, 20 to 29, and then 30 to 39, okay? And within each of the bucket, we have a sorted array. Sorted array is like 1, 4, 7, right? So 11, 13, 18, so on and so forth, okay? Basically, every time when we have a new number, right, we put it into the relay associated, we're going to use a key to a mechanism or like a function to find the bucket, right, this number it belongs to, and then we're going to assign this number to that to its bucket. Since everything is it's sorted, right, inside the bucket, by the way, we're going to use some like sorting method, right, to sort each of the buckets, okay? And then in the end, we simply like concatenate everything together to get our sorted list, okay? So that's that, and we're not using everything in the bucket sorting algorithm here. We're only using the bucket itself. We don't care about what's inside. We don't care about the sequence inside there. So why is that? Okay, so how can we use the bucket sortings, right, to find the bucket idea to solve this problem? And basically, here's how we do it. Let's see. Mm, so we have like a size of the t here, right? Size of the sorry, the difference we're looking for is t, okay? And so that means that the the range of a bucket, right? The range of a bucket is like is t plus one, okay? So what does it means that let's say the range of the bucket we have uh, okay. We have a bucket, and the range of that is is t plus one. So this is also t plus one. This is also t plus one. T plus one. Okay, and then every time when we have a numbers comes in, right, we just use the number, the current number, right, divided by the width of the bucket, so that we can have like index here, right? So that we'll have an index of the bucket that number belongs to, okay? And okay, basically, so the way we are checking it, since the let's say let's say the range is this t plus one. Let's say the index is this one. So this number belongs to this bucket, okay? We have 0, 1, 2, 3, and 4, okay? Let's say the current number belongs to this bucket. And if that's the case, all we need to check is the current bucket plus the bucket 1 and then the bucket 3. We don't need to worry about any other buckets, right? So it's kind of makes sense, right? Uh, because uh, because the range of the bucket is t plus 1. So anything outside of this 1, 2, 3 will definitely like the difference, right, will definitely be greater than t, okay, right? So that's why all we need to check is the previously the bucket on the left side and the bucket on the right side. If there's anything, basically if there's anything in those two buckets, right? Actually, we don't even need to care. We don't even need to care how like which which element in those two buckets, right? As long as there's one element in that bucket, then we know the difference, right? The difference between the current number and that number has to be equal or greater or smaller than t, right? So in that case, we don't even need to keep multiple like numbers in one inside one bucket. We just need to keep one we just need to keep like one numbers for uh per each bucket. Okay. And still we also need to maintain like a size of the case sliding window, which means every time when the uh, when any of the numbers are outside of the sliding window, we just need to move that number outside of the basically we just need to remove that number from our buckets. Okay, cool. Well, actually, you know what? I just realized that here like we're trying to use I, right? But it failed because we can also use I here. It's just that we just need to use I plus one here, right? Because this is the length, it's not the index. I is zero base, right? So so we have to make it one base to a plus one. Okay, so this should just also work. Yeah. So I mean, we can also use the index to remove the basically to remove those like numbers that are outside of the sliding window. Okay, so back to our bucket solution here, right? So like I said, we just need to like create different buckets, and then all we need to compare is just to compare the left bucket and the right bucket if there's any numbers in it. Okay. Uh, cool. So let's try to code that thing. So I'm gonna switch back to Java. Sorry, switch back to Python. And okay, cool. So let's see. Mm, uh, I key. Okay. Mm, width equals to t plus one. Okay. And then we're gonna have a bucket, right? So the bucket is the mm, I'm gonna use like a hash table. So for number in nums, right? So the key, right? The key of the bucket it will be or the index, right? The index of the bucket is the nums divided by w, right? So that's the index. Now we have the index. We have to do a few check here. Basically, if the index the key, let's see, the key is that bucket one is, yeah, so the bucket here, so the key will be the index, right? The value is the numbers in that. And let's see. So yeah, actually, so one more thing. So the reason we're doing like a t plus one, not the t as a width is we want to make sure the left and the right can cover the range of t here, right? So we don't have to go one bucket beyond the neighbors. Okay, so that's the index basically, and if the index, right, if the index is already exists, right, in buckets, okay, then we can simply return true. Okay, yeah. So which means that we already have like the same numbers, right? The numbers within the same bucket, so that we can simply because the reason being is that let's say the bucket size is 4, right? Let's say the t is equal to 3, okay? And the bucket size is 4, so the width will be 4, okay? And then basically, let's say 5, right? So if we have 5, so 5 will go to the bucket 1, right? Because 5 divided by W will be 1. And how about the next one? So that's the smallest number in bucket 1. So what's the biggest number? The biggest number is so 8 will be 2, basically will be 7 for sorry. Yeah, actually 4 will be the first one. Okay. So 4 will be bucket 1 and 7, okay, will also be bucket 1, right? Yeah. So yeah, right. So that I mean that's why we are making the size of W size of the bucket T plus 1 because the beginning and the ending, right? The difference will exactly be the T here. That's why if there are two elements inside the bucket, okay, then we know, okay, they have to be within the range. They have to the difference has to be in the range of T here. Okay, that's why we can simply return true if there's already like an element in the same bucket. Okay, so else, right? So if then another like scenario is we just need to compare with the left neighbor, right? The left bucket, basically, if the index minus 1, okay, in buckets, okay, and the numbers in that bucket is smaller than the W than the T here. So since the size of the W is size of the bucket is W, right? So we have to also compare. Otherwise, if they're on the boundaries of each bucket, right, the difference will be T plus 1. Okay, so that's why we do ABS of the number, right? Minus buckets index minus 1. Okay, it's equal to smaller than T, right? Then we return true here. Or same thing for the right bucket, okay? And ABS, same thing. Plus 1, okay? Return true, okay? And here we just assign that, right? Bucket dot index, okay, equals to num, okay? Same thing if the I plus 1, right, is greater than k. If the length, right, if the length is greater than k, then because again, so I is 0 base, k is 1 base. That's why we do a I plus 1, right? We do delete. We delete the buckets. Delete the buckets of the nums I minus k divided by divided by w, right? That's how we maintain like the buckets of the size of the k numbers. Every time we have a different one, we have a number moved outside of the k size of the sliding window, we remove it from the buckets. And since each bucket only has one number, right? That's why we can simply delete the buckets. And here we simply return false in the end. Okay. Run it. Sorry. Oh, yeah, we don't have I here. Enumerate. Right. Submit. Oh, index W-O. Yeah. So um, yeah, -1. The difference T is -1, which means the difference between the it's -1. No, that's basically if the T is smaller than 0, that's not valid, right? We can simply return false. Okay. Yeah. Cool. So finally, I know this bucket solution is not easy to understand, right? Basically, first, time complexity, right? So the time complexity here, so we are only checking the previously bucket and then the next bucket, so which makes this check here constant time. So basically now the time complexity will be just O of n, right? Space, space same thing, right? Space is like O of the uh, maybe minimum, right? Minimum of n k, okay? So whichever is smaller, that's going to be our space complexity. Yeah, so I know for this bucket solution, it's not very intuitive, but I think you guys can try to understand this, right? Basically, we just allocate the size of the t plus 1, okay, so that we are sure if there are two elements, if we have two elements appears, right, in the same buckets, then we know, okay, their difference is at most t. And then we can also use the left and the right buckets to check if there's any uh, other numbers that can satisfy our conditions. And we're only maintaining one numbers inside of each bucket. Um, yeah, because there's no point of maintaining all the numbers in the buckets, right? Be, uh, I think this part is a little bit tricky to think about, but if you guys think about that, I think it kind of makes sense, right? Yeah, I think I got it. So why we can only maintain like only one numbers here? Let's say we have a bucket here. We have a bucket of 0 to 3, right? And then 4 to 7, right? And then the 8 to 11, okay? So let's say the current number is 9 here, right? Let's say there's a 9 here. The current number is 9. And assuming we have 4, 5, 6, 7, right? Before in the before 9 here, right? So, but the issue, the tricky part here is that we don't have to maintain all more than one numbers inside one bucket. Because why? Why is that? Because every time, as long as we see more than one numbers inside the same buckets, we simply return true here. Okay. Basically, if we have ever seen 4, 5, 6, 7, any two numbers before, right? Any of the duplicated numbers before 9 here, we would have already returned true. So by the time we have 9 here, right? By the time we have 9 here, and we know that, so the previous bucket will at most have one numbers. Okay, that's why we can simply always set this number, the current index with the current number. So because we don't uh, since we don't need to worry about more than one numbers, because it would have already been returned before. Okay, cool. I think that's pretty much I can think about for this problem. Yeah, I hope you guys can learn something from this. And yeah, cool guys. I think thank you so much for watching the videos, guys. And stay tuned. I'll be seeing you guys soon. Bye bye.